Okay, so in this we've got two particles and they're connected over a smooth pulley here, and it's an inextensible string. What we're told is that the slope, the angle of slope in both cases, so this angle here is tan inverse 4 over 3, and this angle here is also the tan inverse 4 over 3. The coefficient of static friction is 1 over 6, and we're asked to find the common acceleration of the particles. Well, just looking at this, those angles are the same. This one is going to accelerate down. We know that because 12 kilograms is greater mass than the 6 kilograms, it'll go down that way. Now, when we get tan inverse of 4 over 3 like that, it's way better to use that. What we know when they tell you that, you can construct a little triangle here. So if this is our angle A, tan A is equal to 4 over 3. So that's the opposite over adjacent, 4 over 3. If you put this into Pythagoras' theorem, you'll get this is the square root of 4 squared plus 3 squared, will work out to be 5. So what it's telling us is that cos A is equal to 3 over 5, and sine A is also equal to 4 over 5. So we're going to be using these in a second here. So this we'll call A, and we know what the angles are. Now first off, what I'm going to do is I'm going to draw the forces here. This one has a force down, its weight. It'll have a reaction force back up, it'll have a frictional force down, resistant motion, and it'll have tension this way. The second body here is very similar. Weight down, reaction off the surface, tension, friction, and that's it for this one. Two of these vectors are of no use to us as they stand. That's that one there and this one here. This vector here, some of the force from it is pulling back down and some of it's pulling in. This vector, we have to split it up into two components, the one down and then the one down the surface and the one into the surface, and similarly for that one there. So I'm going to redraw these over here with those vectors split up. So the 6 kilogram I'll do first here. Now I'm going to be doing a vector down there and a vector down there. That angle there is the same as this angle here, it's always the case there. Similarly, this angle here, A, is the same as that angle there as well. So, where I'm going with this is that instead of this vector here, and I'll just draw it in just to show you that it is, we're going to have a vector down this way and a vector this way. And we're going to replace that one with these two. They're the same, they add up to that one. This one here would be equal to, because that's angle A, this would be the hypotenuse, which is 6g, it's the length of that one, 6g cos A, and this one here is 6g sine A. In fact, you can pretty much work these out, or you can learn them off, is that the component into the surface is always 6g cos of this angle, the component down the surface is always 6g sine of the angle. But you can see from the triangle there that's the case as well. The other forces then are here. We've got tension and friction. So for the 6 kilogram, we might as well finish this off. We have a net velocity, or a net acceleration, that's the net force, is equal to mass times acceleration. And our net force will be equal to tension minus this component of the weight, which is acting directly against it now. So that vector is directly parallel to that one, it's acting against it. So 6g sine theta, which is 6g sine theta is 4 over 5, minus the friction. Now friction is always equal to mu times r. The reaction here, which I forgot to draw in, I should have, is exactly opposite to this component here, exactly opposite to it. The reaction is just pushing back off the table as much as it's pushing into it. So we've got 1/6 times 6g cos theta, which is equal to 3/5. So that will be equal to 3/5g there. So the force of friction then, I can fill that in the next line here. So we have 6a is equal to T minus 24g/5 minus the friction, which is 3/5g. So here we have then 6a is equal to T minus times a minus, that'll be minus 27g/5, because they've got the same fraction. That's our first equation. Now it's going to be very similar for the 12g one as well. So I'll move over here and we'll work through that one. Again, 12g, it's going to be like this here. Now instead of writing the weight vector down, I'm going to write one vector like this and one vector down the way like this. This one always works out to be mg cos theta, or mg times the cos of the angle. Now that's the case, it's always mg cos of the angle into the incline. So in this case it's going to be 12g cos of the angle is 3/5. This one always works out to be mg sine theta. So it's going to be mg sine of the angle. So we just fill that in quickly. 12g sine of the angle was 4/5. Now the reaction is going to be the exact opposite of this one. So I might as well put that in there. It's going to be also 12/3 is 36g/5. That's R. There's two more forces involved. We're going to have tension back this way. There should be just one arrow. The tension back that way, and we're going to have the friction, which is going to resist it as well. So in this, for this one as well, we know the net force is down this way. And I'll just do a different colour. Okay. So the net force, F net, is equal to, and I'll just highlight them all in the blue one here. This one here is what's bringing it down, 12g/4. So we multiply the 12 by 4 is 48g/5, minus the tension, T, that was the tension, minus the friction, F. And if you remember, friction is always equal to mu times the reaction. We know the friction is 1/6, and we know the reaction is 36/5g. So I'll just sub in for friction there, just quickly speed it up there. We end up with 6/5g. Now the net force is always mass times acceleration, so it's always 12a is equal to, and if I bring the t to the left here, I'll have minus t, and then 48 minus 6 is minus 42g/5. That's my second equation. Got my first equation here, and if we just add equation 1 plus equation 2, what we notice is that we've got a plus t there and a minus t there. They cancel really well, so we'll just write this, we'll write them together there. 6a is equal to t minus 27g/5. This one's 12a is equal to minus t minus 42g/5. And what we get is 18a is equal to, they cancel, they add together to give, this one is a plus, is it? There, can I just double check that? It should be plus 42, definitely, thank you. So we get 18a is equal to plus that, 5, carry the 1, 15g/5. 18a is going to be equal to 3g, and a is equal to 3/18g, or a is equal to dividing g/6. And that was the question that they asked us to work out. I'll just zoom out so we can see the whole thing there. The question was to find the common acceleration of the particle and the tension in terms of g. We've got the common acceleration is g over 6. Tension is very easy to work out then. We can use either of them. We might as well use this one here. So sub in g over 6. So we get 6 times g over 6 is equal to t minus 27g over 5. And that should be over 6 there. We get g plus 27g over 5 is equal to the tension. And that would be 5 over 5, 32g over 5 is equal to the tension.